Before I look at types of data, let's look at different types of study. So, a cross-sectional study. In a cross-sectional study, we'll be looking at things at one particular point in time. So we will be observing, measuring, collecting data at one point in time. So the important thing is that we'll say that on this particular day, we had so many cases of this particular disease. So that is a cross-sectional study. A retrospective study. So in a retrospective study, we are looking in the past. So we're going backwards in time. We're examining records, interviews, etc., backwards in time. So an example of a retrospective study is a case control study. So in a case control study, we divide our population into two groups, cases and controls, and then we pick a sample from each of those. So our cases are people with a particular, let's say, disease. Our control would be people that do not have that particular disease. And so maybe, let's say, in a case control, we have people who have lung cancer. And our controls are people who do not have lung cancer. Now, when we do our case control study, we would try to make the cases and controls look relatively similar. And the only thing that should be differing is that the cases have lung cancer and the controls do not have lung cancer. We then look back to see what have you guys done over the past couple of days, months, years. So we look back, well, for lung cancer, you look back years. So what have you been doing for the last several years? And so we then examine, their records, medical records, things like that. And we do conduct interviews. We say, so, what do you guys eat? Do you guys smoke? Don't you smoke? Where do you guys work, etc. And so we then look at those, and that is a case control study. It is retrospective. We're looking backwards in time. We're telling you, what did you guys do for the past 12 years? What have you guys been doing with yourself for the past 20 years, 30 years? Retrospective. A prospective study. So in a prospective study, well, we go into the future. And so we'll be going into a future with a prospective study. An example of a prospective study. So sometimes this is also called a longitudinal study. What was it, 20 and up, or I think. There's this one series, British series. It was 7 and up. I think it's 7 and up. That's it. If I don't know if anyone has seen this series, where it's called 7 and Up, where they looked at. So this is a longitudinal study. They looked at people at age 7. They came back, and this is actually like a movie or a series. You look at people age 7, at age 14, age 21, etc. Every 7 years, up until, what did they end? They ended when they were, well, when everyone in the study died, so in the 70s and 80s or whatever. It was a very long study. So there's a series, you can look at it. So it's a longitudinal study. It's actually interesting. So that's a prospective study. Also have something called a cohort study. So in a cohort study, well, you have these cohorts. And so these are people, well, so you divide your population into 2 pieces. Exposed, so you have some sort of, let's study, you want to study smoking. So let's study smoking. So I'll take people who smoke and people who do not smoke. And I will then pick from each of these groups, so this is my cohort of smokers and my cohort of non-smokers. I'll then look at each of these, and for the next whatever, how many years, we will then take data and see what happens to each of these groups. And so, this exposed group and this non-exposed group. That is called a cohort study. It is a prospective study. So these are types of observational studies. All you're doing is observing your subjects. You're not interacting in any other way. You're just observing what's happening and seeing what is currently occurring, what has happened previously, or what is going to happen in the future. And so, in an observational study, we observe, but we do not modify. In an experimental study, we modify. So, observational study, you observe and measure, but you do not modify. What are the different types? Yes, question.
Yeah, in the prospective studies, there is still a control group also.
Say again.
In a prospective study compared to a retrospective study, there are still control groups, not only case groups, right?
Well, that is one type of retrospective or prospective study. So a prospective study just means you go forward in time. A retrospective just means you go back in time.
Yeah, but the groups, we still need the control groups in a prospective study.
Well, not necessarily. Not necessarily. No. Okay, that in other words, that's for a case control study.
All right, thank you.
So most retrospective studies are case controls, but it's not necessary, right? So the majority of retrospective studies are case controlled. The majority of prospective are cohort studies, but they're not the same term. They're just the majority of times. So to figure out which one is which, you look at when are the observations made. If they're made forward in time, it is prospective. If they're made just at one particular time point in time, cross-sectional. If they're made in the past, retrospective.
Okay, got it. Thank you.
And all case control studies are retrospective. All cohort studies are prospective. Okay? And that's a way to think about it. But, you know, a retrospective study doesn't have to be case control. Okay? Just that the majority are. Okay, so I guess I should say this. If sample data are not collected in an appropriate way, the data may be useless. So we will be assuming throughout this course that the sample data has been collected in an appropriate way, and we'll actually be assuming that it's of a particular type of collection method, simple random sample. So we'll be assuming it's a particular type of sample and that it's done appropriately. But in real life, that of course doesn't happen. We're just assuming that it happens so that we can do mathematics on it. So in later courses, when you are in a particular major, they will give you research methods to hopefully tell you how to properly collect and conduct your studies. So how to properly collect data and how to properly conduct studies. So, as I said before, there are really two types of ways of obtaining major types of ways of obtaining data through either an observational study, which we just looked at above, or experiment. So in an observational study, we are observing, measuring specific characteristics without attempting to modify the subjects being studied. So, for example, the Pew Research Center surveyed 2,252 adults and found that 59% of them go online wirelessly. Is this an observational study? Well, is this observational? Did we do anything to them? The answer is no. So therefore, yes, this is an observational studies because the adults had no treatment applied to them. You were just, finding how many of them go online. In an experiment, you apply some treatment. So that's the difference between an experiment and an observational study. In an observational study, you do not modify. So it's without modification. Whereas in an experiment, we give some treatment in order to modify the subjects. So we apply some treatment and then observe the effects on the subjects, the experimental units. So we apply some treatment and proceed to observe its effects on the subjects. So in the largest public health experiment ever conducted, 200,745 children were given the Salk vaccine. Another 200,229 children were given a placebo. Is this an observational study or an experiment? So, back in the United States, prior to 1940s, during summer, there would be these gigantic waves of children, mostly young people, children, usually between the ages of like 9 to 18, 19 years old, who would get polio. So they would contract the polio virus, and they would proceed to become ill. So the majority of people who contracted the polio virus had very, very minor symptoms, but they would go on to infect other people. And some of these children would then get severe reactions, and they would have permanent paralysis, either of their whole of their lower half of their body, usually their their legs, so they would not be able to walk, or they would even not be able to breathe. So a lot of these children, young adults, would then have to spend the rest of their lives in what was something called an iron lung. So it was an iron lung where they would get in this, it's a cylinder, and it had some sort of membrane that would pressurize and depressurize to move your lungs up and down. Your rib cage, it would move your rib cage up and down so that it would allow you to breathe. And so these people would need to stay years upon years and decades in these iron lungs in order for them to breathe. So because of this, there was a campaign that was meant to rid the United States, actually North America. It was actually mostly North America. Let me not just say United States, so North America, well, just US and Canada. So to rid the US and Canada of polio. And so there was a campaign started called the March of Dimes. Has anyone ever heard of the March of Dimes? Currently, the March of Dimes is still around. So the March of Dimes would go out and ask people to donate one dime. And so they asked, and most families and children even gave a dime, because it was very evident that a lot of people were getting ill and spending their lives being crippled due to this. And so the March of Dimes funded these research, and one of the research outfits with Salk, with Jonas Salk. So Jonas Salk came out with the Salk vaccine. Sabin also came out, but that was a little bit later. And so, like a few months later with Sabin, the Salk vaccine. And so they actually did the following experiment. They gave 200,000. It was actually supposed to be 1 million people. They're supposed to give, I believe, 1 million children the Salk vaccine, and another million children were supposed to be given basically nothing. They were just injected with saline solution. And so, and then they observed what was happening. So is this an observational study? So they then would observe to see if these children here that were given the vaccine, if they, would then develop polio. And then they looked at these other children who were given this placebo and see if they would then be, develop polio. So is this observational or an experiment? What do people think? Let's see. Oh. Jonas chapters 1. Yes, okay, so I'll answer that too. Anyone, what do you think? Was this an experiment, or was this an observational study? How many people think
experiment?
It is an experiment. So this is an experiment because the vaccine constituted a treatment, because they were somehow trying to modify a subject. They were trying to see if, this vaccine would make a difference on getting a, polio or not. Here's a question. Does anyone see any possible ethical issues with this study?
Yes, subjecting 201,000 plus children to the sickness.
That's right. So very good. So the problem is, and this is why there were supposed to be 1 million people that were done in each of these groups. The study was cut off because what happened is they found that virtually none of these people got polio. It was like, 99.9% of these children did not get the polio, whereas the normal number of people here, normal number of children, got polio. So when they found those results, they stopped the study. So they actually stopped the study saying, we're giving everyone the vaccine. So they stopped the study midpoint and saying, okay, we will give someone the vaccine. Okay, good. So, a response variable. The response variable is the variable being studied by the experimenter. So an experiment investigates how the response variable behaves when the investigator manipulates one or more of these factors. Any particular specification of a factor is called an experimental condition or treatment. So, an extraneous factor. An extraneous factor is a factor that's not of interest in the current study, but it's thought to somehow affect the response variable. We try to somehow get rid of extraneous variables. So we will use these extraneous factors to create experimental groups that are similar with respect to those factors, thereby filtering out their effects. So we want to somehow get rid of these by factoring on those extraneous factors. So we create the experimental groups similar with those factors so that we can filter out their effects. So differing designs of experiments, randomization. So in randomization, we select subjects to different groups through a random selection. So in a comparative experiment, subjects are randomly assigned to groups called randomization. Let me do something for 1 second. I just remembered. Someone asked me, do you have access to lecture notes? The answer is yes. So this is section 1.2, right? So you would click here. So there they are right there. So here it is. So let's see, where were we? Right here. No. Right there. So these are the lecture notes. So the answer is yes. You do have access to these. They're just found by clicking where it says click here for the PDF. Or sometimes they just have it where it's highlighted under the name of the particular section. Okay. They're locked. Oh, yes. So they are locked. If you see, there's a prerequisite. So you'd have to mark any of the prerequisites as done. If you don't, then yes, they are locked. So you need to, if you didn't look at those, then they would be locked and you couldn't, you can't look at these things. Oh, you can't even do that? Ooh, I shouldn't have done that one. So you need to actually mark these things as done so that you can go on to look at those lecture notes. So then they are, yes, they are now available for you to look at. Okay? Will the recording be posted on Canvas? Yes. Obviously not at this. By the way, these are previous recordings of me. So you can hear me talking in the background.
You're giving them sort of drug.
Okay, so those are previous recordings. If you look under Zoom, oh darn. If you look under Zoom and you see here where it says cloud recording, you click on cloud recording, and unfortunately there's nothing there because this is the first meeting. So there's nothing there because we haven't met yet, but there would be stuff here if we have met previously. Let's leave student view. So let me go to a different course. 263. I know I've met 263. So if you click on Zoom, you don't see this because that's an iPad. If you click on cloud recording, here are the cloud recordings, and you would click on a particular date, and you could listen to the recording and download it. Okay? So the answer is yes, they are available. You just have to, oops, I'm in the wrong class now. Yes, they are available for you to look at. Okay? Good. I think I answered all those questions. Replication. So actually, in comparative experiments, subjects being randomly selected, randomly assigned to groups is called randomization. Replication. Replication is the repetition of an experiment on one or more subjects. Well, on more than one subject. Your samples should be large enough so that erratic behavior is minimized. A comparative experiment. In a comparative experiment, the group of subjects is randomly divided into two groups. And these two groups should be equivalent as well as can be done. The experimental group and the control group. In the experimental group, they'll be receiving the treatment. In the control group, they will not be receiving a treatment. The fact that you do not, a non-treatment is called a placebo. So the experimental group gets a treatment, the control group gets a non-treatment, a placebo. So a non-treatment is called a placebo. A placebo effect. So the placebo effect is when this control group, the one that does not receive a treatment, has a positive response to the non-treatment. So having a positive response to a non-treatment is said to be a placebo effect. If you are looking at, especially, let's say, the pharmaceutical industry, these effects can be extremely large, nearly as large as the positive effects for the experimental group. It's amazing how large they are. So when a subject in the control group has a positive response to a non-treatment, we call this the placebo effect. One way of attempting to minimize some of the problems with, well, these extraneous factors is a technique called blinding. And so in single blinding, we will not tell the subjects if they are in the control group or the treatment group. We will not tell the subject if they're receiving a treatment or if they're receiving a non-treatment. In a double-blind experiment, we will not tell the subject that if they're in the control group or the treatment experimental group, we will not tell the subject if they're receiving a treatment or non-treatment. And neither will we tell the researcher. So we'll not tell the experimenter if they are in the control group or if they're in the experimental group. So the person who is giving you the treatment doesn't know if they're giving you a treatment or a non-treatment. That is called a double-blind experiment. A triple-blind experiment is when the subject, the researcher, and the analyst, the person who is analyzing the data, the statistician who analyzes the data, also does not know if the subjects are in a control group or the experimental group. So they do not know if the particular subject got a treatment or if they got a non-treatment. And so that's a triple blind. Confounding. Confounding occurs in experiment when the experimenter is not able to distinguish between the effects of different factors. You try to eliminate confounding through proper experimental design. So one way is doing randomized block design. So you will block your subjects into these groups. They're very similar. In matched pair design, you will try to match a subject in, well, a treatment group and a control group, and you try to match them as best as possible. The way I usually think of this is in a diet. This is the easiest way to think about it. So before the diet, it's the same person. So I'm going to match with myself before I'm on the diet and after I'm on the diet. So a before and after. And that's a matched pair, because certainly you're very, very similar to yourself. And so because of that, I'm able to match you with yourself. And the only difference is that, you know, this was you before you went on the diet, and this is you after you started or finished the diet. Okay, so that's a matched pair design. So there are different types of errors that can occur. A sampling error. So in a sampling error, these result from just chance fluctuations. So the fact that, you know, you're taking different people, well, not everyone's the same. We're not all clones of each other. So there's a little bit of fluctuation. And that's just due to random fluctuations. And so that's a sampling error. So it arises from the fact that there's a difference between a sample result and the true result. And this results from just chance sample fluctuations. You can minimize this by taking a properly large, not too large, sample. So if your sample is too small, you could have large sample fluctuations that will overwhelm your results. And if your sample is too large, you can also have confounding variables that will affect your results. So, well, the non-sampling errors will then become too large. So, non-sampling error. Non-sampling error occurs from incorrectly collecting, recording, analyzing data. This could be due to, let's say, a defective instrument or copying data incorrectly. So you should never have non-sampling error. So these non-sampling errors should never occur, but in reality, they occur a lot. So in one of my previous lives, I was the head. I ran the math placement office for a district. So I ran the placement office, and I was actually I believe the only person in the district that had records. I was able to see and modify all records for all students in the district from the past, from currently and in the past. So I had all access, free access to all records of all students. As I think there were only 2 people in the district, and I was one of the 2 people. So I think I was the only There were only two people. The person next to me in the next office and myself had complete access to all student records. And I was utterly amazed at how many errors, how corrupted a database can become. So students seem to always input their phone number for everything. So where you're supposed to have, say, your student name, they would, if you look at it, some student names were their phone number. Other times you'd look for their age. Their age would be in the whatever millions of years, again, because they put in their phone number or even, and so, and of course, even though I was able to modify student records, you don't modify student records unless it's almost by court order. You once you have you should not modify a student record unless there's a really, really, really important reason why you modify a student record. You want these to be permanent and not to be touched. So and once it's in the system forever, basically, because you never want to modify it. So there are all these students with, ages in the millions of years that are going around. Again, but those were easy to tell, and easy to modify. You just get rid of, don't look at students whose ages are more than, usually, like you say, 1,000 years old, or negative. We don't want to look at students whose ages were, negative or, greater than 1,000 years, because you're certainly sure that those are errors. So you got rid of those errors. So there are these errors. I also was looking at, malpractice data. This is differently for a different reason. And it's amazing how many errors, mostly errors due to not inputting data, that doctors would do because they don't have enough time. So a lot of the malpractice data is corrupted due to, again, data input errors. Okay, so a properly designed study should report the following: a description of the sample population, description of the method of contact, response rate, exact wording questions, timing of the interview, the margin of error, size of sample, sampling techniques. So you should consider your population, method of contact, response rate, wording of questions, timing of the interview, and the sample design. So in a statistical study, you prepare, you analyze, and you conclude your study. So let me give an example. In a test of the Atkins weight loss program, 40 subjects had a weight loss of 4.6 pounds after 1 year. Using formal methods of statistical analysis, we conclude that diet appears to be effective. However, although 4.6 pounds is statistically significant, using common sense, it does not seem to be worthwhile. I was also looking at, this is for medical research. I was looking into Alzheimer's disease. And so they had a particular treatment for Alzheimer's. So Alzheimer's disease, I'm assuming people know what Alzheimer's disease is. So Alzheimer's disease is a neurodegenerative disease. It is a disease that attacks your brain, the neurons in your brain, the things that make you think, that give you memory, or that allow you to speak and walk and breathe, things of that type, and to have your personality. This disease attacks those systems. And so it is a very slow disease, taking about 30 years. And it is 100% fatal. So it has 100% fatality for this. There are currently no treatments. Well, there are treatments. So I was looking at one of them they're based. One of the problems with Alzheimer's is they really don't even know what it is. So there are a lot of problems. They have no idea what the disease is, how it progresses. I mean, there's a lot of theories, and they've been doing a lot of research for the past 40, 50 years, but they still don't quite know what's going on. And so one of the major hypotheses is the amyloid cascade hypothesis. And so there are these proteins, that build up in your brain that can be seen in an autopsy and is noticed in diseased brains. It's also noticed in non-diseased brains, but not in the same quantities as in diseased brains. So these plaques are built up, and they have treatments to reduce the number of amyloid plaques, these caused by this beta amyloid protein, and the precursor protein. And so that are caused by this type of chemical. And so this particular treatment did reduce the amount of amyloid in subjects, but after treatment, they found that it is statistically significant that the average life of a patient taking this particular treatment survived for, I believe it was an average of 8 days longer than those without a treatment. Now, if you're talking about a person's lifetime, that is not significant. That even though it's statistically significant, who cares if I live, well, I guess, in a lifetime, 8 days or whatever is not really something that's, very large, especially due to the fact that there are side effects to the treatment. The brain swells and other things. It also Yeah. So there are a lot of other bad things, you know. The fact that it gave extra days is good. But the fact that it also, you know, had months of excruciating outcomes for giving the treatment is not worth the treatment, the benefit. It's not, the pain is not worth the benefit. So next. So things can be statistically significant. So in this class, we're going to be doing things and I'm going to say, oh, this is statistically significant. And that really is all I'm going to say. But once you exit this class, there may be other things to consider besides statistical significance. There's also a practical significance. And we're not going to do that because there's no way for me to know what you are looking at to see what is practically significant. What makes something okay. So, potential pitfalls. Misleading conclusions. So, and this is said a lot. So, concluding that one variable causes the other variable, when in fact variables are only correlated or associated. And so the problem is that people hear that there's a correlation between these objects. And they think that, when epidemiologists, when the CDC says that there's a correlation, people think that then that means there's a cause. The answer is no. Correlation does not imply causation. So a correlation is merely a correlation. So there's a correlation. So things like, so two variables may seem to be linked, such as smoking and pulse rate. There's a correlation between them, but you cannot conclude that one causes the other. There may be many reasons. In other words, there has been shown this correlation, but there are other lifestyle reasons why these occur. Okay, so more potential pitfalls. If your sample is too small. So if you have a sample that's too small, then you cannot base conclusions on this, such as basing a school suspension rate on only a sample of 3 students. This is done a lot with rare diseases. So unfortunately, with a rare disease, you don't have a lot of things to go with. And so because of that, your conclusions might be incorrect. Loaded questions. So if sample results are not worded carefully, the results can be misleading. So 97% said yes to the following question. Should the president have the line item veto to eliminate waste? Actually, I remember this question. Next. Another survey came out like a few days later where it said 57% said yes to the following question. Should the president have the line item veto or not? So the fact that they were saying to eliminate waste obviously biased the answer. So it was not 90, it was, this is a loaded question. Now this one is harder. So, and well, in math, we know this happens a lot. So questions are unintentionally low by such factor as the order of the item being considered. So when the question was, would you say traffic contributes more or less to air pollution than industry? The results were 45% said that traffic did, 27% said that industry did. They re-asked the question. They did another sample and they asked in the following order. Would you say that industry contributes more or less to air pollution than traffic? When stated in this fashion, 57% said industry and 24% said traffic. So they were saying yes to the first option. And so what you'll notice is that there is a bias where if you give people two choices, they pick the first. If you give them like 15 choices, a lot of choices, like 5 choices, they pick the last one. So the problem is that when people are given 2 choices, almost everyone, more people say the first choice, just because they do. So more people pick the first choice when given a choice of 2 questions. So if you're given 2 options, more people will say the first one. And so they pick the first one because they do. That's what people pick for first choice in the option of 2. They're more biased toward the first.
So how do you ask the question, such a question?
Well, haven't you ever been to the eye doctor? So when you are at an eye doctor, they say, okay, which one do you pick, this or that, right? And they keep changing. They have that huge, weird looking thing on your face, right? So what they do is they say which one, first or second, right? And then what you do is you give them, basically they're doing it where they ask the same question more than once in both orders. So what they're doing is they're cycling through all questions in all orders. So what you have to do is reword them yet again. We're asking the same question, but so people don't know you're asking the same question, but in a different order. So this is hard. It is harder to deal with this pitfall than other pitfalls because the order makes a difference. So what you have to do is re-ask the question yet again in a different order, in the opposite order, but in such a way that people don't know they're asking them the same question. The way the eye doctor does it. So the eye doctor cycles through, and that's why they don't care which one you're picking. And they say, do it really fast. Tell me, they flip it really fast. So, right, this or that, this or that, this or that. And then they go next one, this or that, right? And then they cycle through it, and the cycling through asks you the same question more than once, but in a different order, right? And that's what they're doing. Okay. Next, non-response. So non-response. So this occurs when people refuse to ask, to answer, to respond to your survey. So when I was a freshman, there's a freshman. When I was a freshman in college, I was taking is that sociology? Yeah, a sociology class. So it was a class in sociology. And one of the things they had us do was to do a phone survey asking people questions about personal questions about relationships and things of that sort. And I called 100 people, and I found out that if you are a student asking a question on a phone, no one answers the question. And so usually what happened is I would say, hello, I'm a student at University of California. And before I even got through with that, they would hang up. So usually they would hang up when I said, hello, I am, and they just hang up. So I believe of 100 people, there was only one person who partially answered the question. So the response rate was very, very low. Sometimes the way that they deal with this response, the fact that no one wants to respond to a study, is sometimes they give participants money, a very small token. So sometimes they give them like $10 or $15 to complete the survey. So if you've ever, well, I don't know, I don't go to the mall that often, but I've been at the mall when someone asked me, hello, do you want to do a survey? And they said, if you complete this survey, it will take like 15 minutes and we'll give you $15. And I said, sure, okay, $15 for 15 minutes, I'll do it, Now, of course, the problem is you want it to be a nice random selection. And if you give people too much money, then they are not going, then the reason that they're answering these are because they want the money. So you can, unfortunately, giving people money is problematic. But if you don't give them money, they don't respond. So the way we try to do it is to give them a little bit of money, but not too much money, to be able to sort of, deal with this non-response rate. Another potential pitfall is missing data. And so this can affect our results tremendously. So example, people with low incomes are less likely to report their incomes. In the US Census, if you're homeless, if you have low income, if you are, a immigrant with non-legal status, then you're less likely to participate in the US Census. Here's an example. At the I'm in class, kitty. I'm sorry. The cat came down. She wants food, so she hissed at me because I'm not giving her food at this moment. Okay. They don't understand. So, missing data. HIV, AIDS. When it first was found to be a disease, for the very first months, people looked at the data, and when they looked at the data, they did this cohort study, And they found that people, everyone, almost everyone who was infected with HIV had extremely mild, non-severe, outcomes, that the disease was extremely mild and with very few, if any, minor effects. Now, the problem was that almost everyone died. So the problem is that the only people that they found in the records that were still alive after they did this every 3 months. After 3 months, were people who had extremely mild conditions and reactions to HIV. And so, unfortunately, the missing data, the fact that there are all these non-participants because they died of the disease, gave extremely misleading results. It isn't that the disease is mild, it was that the disease was killing everyone. And that was the reason that everyone had mild reactions, because those were the only people that responded. Everyone else had already passed away. Next, precise numbers. So, in this class, when you do calculations, I will ask you to write all the digits that you see on your calculator. And so I'll ask that. But do not make the assumption that this means that these results are accurate. So just because a figure is precise, do not incorrectly assume that it is accurate. So precise numbers can still be an estimate. Everything that we do in this class is an estimate. Well, almost everything we do in this class is an estimate. So all the statistics deals with estimates. And so because of that, I will merely put equal signs. For everything I write, I'll write an equal sign, but it really should be approximately equal to. So in statistics, we write equal signs to mean approximately equal to. We're always doing some approximation. Percentages. Percentages can be extremely misleading. I always notice that, especially like in Wall Street and all that, they're always only interested in percentages. But what this means is that if you're extremely successful, you have a very low percentage change. So if you're a very large company, it's hard to get a 100% increase in your revenue. If you are selling a very, very successful item to everyone in the world, it's hard to double your revenue to make everyone buy two of your products rather than one of your products, or 4 of your products rather than 2 of your products. Whereas if you're a small company where you only sold 5 objects, well, next year you can buy, if you then sell 10 objects, you double your revenue. So that's really easy to do. So it's very misleading when people say things like percentages, and sometimes it's unclear what a percentage means. So we've already improved 100. So this was a continental ad. We've already improved 100% in the last 6 months with respect to lost baggage. So what the heck does that mean? You know, with respect to what? Okay, so let me talk about variables, but let me give you guys a 5-minute break so I can feed the cat. Okay, let me give you guys a 5-minute break here till 10:25. Let's start back at 10:25. Okay. So yet another attempt to define random variable. We will have yet a third attempt later that will give a much better, I think in chapter 4, a much better definition of random variable. A random variable is a function whose domain is called the sample space. For example, I wish to know the heights of students in this class. So height, in this case, will be my random variable. Data is a particular instance, a numerical or categorical value of the variable. So say I want to find the height of students in this class. So things like 5 foot 4 inch, 5 feet could be, heights for students from this class. I will size variables or data. So quantitative variable will have results that will result in, quantitative data. So I'll either say, so you should either think when I say data, it's either data or variables. I can categorize variables into 2 different cases, quantitative or qualitative. Quantitative data is data that is numerical in nature. So it's numerical in nature. So it will, result in counting some sort or measuring some sort of result. Things like the weights of supermodels, the ages of respondents. Qualitative data, sometimes called categorical or attribute data, is data that can be separated into different categories that are distinguished by some non-numerical characteristic. So quantitative data is numerical in nature. Qualitative data is non-numerical in nature. So things like gender. So let's say male, female of professional athletes. So that is qualitative. You can't put, your gender is not a number. If someone says, what's your gender? And you say 43, that doesn't make much sense at all. It's not a number. Your gender is not a number. Short number. So just because it's a number does not mean that it is quantitative. So a shirt number on a professional athlete's uniform. So if I have this football player, his shirt number is not quantitative. It is not numerical in nature. The shirt number here just is a substitute for his name. And so the fact that you have, you want to put the name of your player on your jersey, well, since you're, some people are way, way far out in the bleachers, they're, half a mile away or whatever, not quite that far, but they're way, way far away from this actual person on the field. They're not going to be able to see and read your name. So therefore, they give gigantic block letters so that when you see these block letters, you can look up in your, your program that you may have for the game, and you look up and say, oh, this is so-and-so, because you know that their number stands for this particular person. And so short numbers are actually just names. And so a name is qualitative. And so this jersey number here is qualitative because it's really just a name. It is the name of the player. So qualitative are non-numerical in characteristic, whereas quantitative is numerical in characteristic. So just the fact that they are numbers or they're, well, non-numbers, rather than saying that, really is the nature of the object numerical than it is quantitative, is the nature of your value non-numerical than it is qualitative. So I can further subdivide quantitative data into discrete data and continuous data. So I'm going to subdivide my qualitative data into discrete or continuous. With discrete data, we count to obtain the data. And so if you're counting to obtain your data to determine the value of your variable, then your variable is discrete, such as the number of eggs that a hen lays. If instead you measure to determine the value of your continuous variable, then this is a continuous variable. This will be continuous data. So the amount of milk that a cow produces, 2.343115 gallons per day. Now, if you're measuring, you need an instrument to measure. And so your instrument in this case is, well, you're using this, I don't know, this gallon jug, right, to tell me how many gallons that this particular cow produces. How many gallons of milk that this particular cow produces. This amount depends on your measuring instrument. So if instead of saying gallons per day, I want liters per day, this value is different. And so this number depends upon a measuring instrument. And so if your result depends on your instrument that you're measuring, then this is continuous. Whereas if this result does not depend on an instrument, then it's discrete. No matter how you measure, the number of eggs is always going to be the same. I don't care what you're doing. This is the number of eggs. You're just counting number of eggs. So this number of eggs that you're counting does not depend on an instrument. And so this is non-dependent on an instrument. Therefore, it is discrete data. So the number of eggs that a hen lays is discrete data. So number of students in class, is that discrete or continuous?
Discrete.
Discrete. Yes, they do. Okay. How about age? Is age discrete or continuous? 19, 20 years old, 30 years old. Is that discrete or continuous? Your age.
It can be both, depending on how you measure it.
No. Well, notice what you just said. How you measure. If it depends on how you measure, then it is continuous.
Continuous.
Because you said it depended on how you measured it. if you measured it in days, in years, in centuries, you know, that's you're going to get a different results, right? And so, you know, therefore it's a continuous variable. How about Social Security number?
That's discrete.
No. Social Security number?
Isn't it discrete?
No, not discrete. It's a trick question. Social Security number. It's not numerical. So it is qualitative.
Yes.
Because it's your name. It's a very it's a number, but it's really your name. So it's unique to yourself. So it's a name.
It was a trick question.
It was a trick question. It was a trick question. So it was a trick question. Occasionally I will give you trick questions. So it's actually not, it's not quantitative. Therefore, it's not continuous or discrete. It is qualitative. It's one of the choices I didn't give you. It was qualitative. Okay, so I don't do that on tests, just in class. Levels of measurement. So, so one way of, you know, classifying data is see if it's you know, numerical nature or non-numerical nature. Another way, and this is completely separate, a different way of trying to classify data. This is only for data. This is not for variables. So the previous one is classification that was the same for both variables and data. This is only the levels of measurement are only for data. And so it's a way to classify data. It is the amount of mathematics that can be performed on the data. So this classification depends upon the amount of data that you can perform on the data. Okay, so there are 4 levels of measurement: nominal, ordinal, interval, and ratio. And so nominal, ordinal, interval, and ratio. And as we proceed, nominal, ordinal, interval, and ratio, this is sort of the most basic. We then add something to nominal to get ordinal. We then give additional structure to get interval, additional structure to get ratio. So obviously something that's ratio has the same quantities plus additional quantities as nominal, etc. But you'll call it ratio because you always look at the higher of these. So nominal. In nominal data, you're only looking at, well, can I put it in some set? So set membership. Nominal levels of measurement is categorized by data that consists of names, labels, and categories only. So that's the only structure. You know, I know your name, I know your label, I can tell what category you're in. The data cannot be arranged in any sort of ordering scheme, such as low to high. You only know set inclusion. That's it. So the nominal level of measurement classifies data into mutually exclusive, non-overlapping, exhaustive categories, meaning that you're allowed to, you can place any data value in one of the categories in which no ordering or ranking can be imposed upon the data. So with nominal data, only set inclusion can be determined. So the only mathematics that we can do is set inclusion, nothing else. So an example, survey responses, yes, no, undecided. So I can tell if the person said yes, no, or undecided, but that's it. So I don't know anything else about you. If the only thing I know about you are the survey results. I can only tell if you are in one of those categories that said, yes, or you're the category who said undecided. Okay. Next, ordinal data. So ordinal data will include something to the set inclusion, some additional structure. So data at ordinal level of measurement, if they can be arranged in some order. So we have some ordering to our set. We can completely order the set. But differences between data values cannot be determined or are meaningless. So ordinal level of measurement classifies data into categories that can be ranked. However, precise differences between the ranks do not exist. With ordinal data, the set is totally ordered. However, differences between two elements of the set is unable to be defined. So that is ordinal data. Order. There's an order on it. So you have ordinal data if there is an order. Nominal data if you only know the name. So nominal, name, ordinal, order. So things like course grade, A, B, C, D, F. So I can say, oh, you're in the category of A. You're in the category of D. There's an order. A is bigger or better than D. So there is a order here, but I can't tell, what's a C minus an A. Is a C minus an A? Is that difference? A B? Is it a D? Is it an F? Is it an A? I don't know. You can't tell differences. These are some range of values. So I can't take differences in between these. It makes no sense at all. Okay. Interval. So interval data. So in addition to having the set that's ordered, completely is totally ordered, we have the additional property that there is a difference. So differences between two data values is meaningful, has meaning. Get rid of the less. So it has meaning. However, it does not have a natural zero starting point where none of the quantity is present. So the interval level of measurement ranks data and precise differences between units of measure do exist. However, there's no meaningful zero. So with interval data, the differences between two elements. So with interval data, the difference between two elements of the totally ordered set is defined. However, scalar multiplication is unable to be defined. So things like years, the year 1000, the year 2000, the year 1776, the year 1492. So the year 2000 is not twice, 1,000, or you can say that, well, look, I certainly can put a ordering on this. I can say, well, 1,000, then 1,492, then 1,776, then 2,000. So I can figure out an ordering on this. And of course, I can figure out membership, set membership. You're in this particular year. But let's say the year 0. If I look at the year 0, does that mean that that was, that there was no time at that year? And the answer is no. It's just an arbitrary number, 0. So 0 doesn't mean none in this particular case. And again, things like, the year, 1,500 in the year 2000 is not, 25% more than, the year, 1,500 or whatever. It's scalar multiplication doesn't make any sense in this case. Okay. Let's talk about temperature. Actually, that's better. If you, let's say, have a temperature of 10 degrees and a temperature of 20 degrees, okay, well, and let's say this is in Fahrenheit, 0 degrees Fahrenheit. Well, does 0 degrees Fahrenheit mean that you have no temperature? So is 0 degrees Fahrenheit no temperature? And the answer is no. What is 0 degrees Fahrenheit? Does anyone know? What is 0? Yeah.
0 degrees centigrade is the temperature of ice.
Yeah, for centigrade. Yeah, for Celsius. So for
32
Celsius,
plus, it's 32 plus.
Yeah. So for Celsius, 0 degrees means 0 degrees Celsius is the freezing point of water at 1 atmosphere, and 100 degrees Celsius is the boiling point of water at 1 atmosphere. What is 0 degrees Fahrenheit? Don't know. So 0 degrees Fahrenheit is whatever, right? It's 0 degrees. It doesn't mean anything. But actually, I guess the way that Fahrenheit was a person, by the way. The way that Fahrenheit determined, and Celsius was a person too. So Celsius is a person. They both knew each other. They were both contemporaries of each other. So so Celsius was like, well, let's do a temperature scale according to water. The boiling point of water and the freezing point of water. And Fahrenheit was like, well, who cares about water? I don't care about water. I care about people. And so his idea was that 100 degrees would be the temperature of a human body. Of course, he's wrong. It was not, it's less than, people usually, 100 is actually warm for people. So he was saying, well, 100 should be, that's sort of the typical temperature you get, a hot temperature. So that's a hot temperature, good temperature of your body. And 0 degrees, the way he figured that out is, that's cold. So 0 degrees was what he thought of as cold for the, this is like really, it's the coldest you want for your human body. And so he thought 0 to 100 should be the typical range that you want your temperatures to be in. So if you notice that it's not typical that when you look at the temperature outside that it's more than 100, and it's also not typical when you look outside that your temperature is less than 0 degrees. And so most people live in regions where negative temperatures are uncommon. There are very few places, actually, even in the United States, where temperatures ever become negative, and very few well, it's becoming a little bit more common. And there are very few places where it is, semi-common to have temperatures over 100 degrees. Okay, so 0 degree does not mean no temperature, neither in Celsius or in Fahrenheit. 0 degrees was some arbitrary thing that was picked for both Celsius and for Fahrenheit. Or centigrade, which is the same as the Celsius. Ratio data. In ratio data, well, we have the same as interval data, but there is a natural 0 starting point. 0 indicates that none of the quantity is present. So both differences and ratios are meaningful. And so there exists a true 0. With ratio data, the difference between any two elements of the totally ordered set is defined, and so is scalar multiplication. So, example would be height of students. So, a person that is 4 feet tall is, well, let's say 6 feet. A person that's 6 feet tall is twice as tall as someone who's 3 feet tall. And a person that's 0 feet tall or 0 inches tall has no height. Obviously, it's not a person. But if you had a height of 0, you would have no height. Let's talk about weight. That might be easier. So if you have a weight of 0, then you are weightless. If you have, let's say, a weight of 100 and someone else weighs 200, then the person who weighs 200 is weighs twice as much as the person who weighs 100. And so that is ratio data. Price of college textbooks. And so $0 represents no cost. So if you say the price of your textbook is 0, then it has no cost. Price of $100 textbook is twice as much as a $50 textbook. Kelvin. So in Rankine. So there are temperature scales such as Kelvin scale and Rankine scale. Has anyone ever heard of Kelvin or Rankine? I mentioned.
Yes.
Yeah. I was thinking you did. You probably know. You definitely know Kelvin, right? I don't know. Do you know Rankine?
No, I heard of him, but I don't. I forgot.
Yeah. It's the American one. It's the Fahrenheit one. That's why you don't know it. So Kelvin is where 0 degrees means no temperature. Of course, what does temperature mean? So temperature is defined as this random movement of atoms. And so at 0 degrees, there's no random movement of atoms. Okay? And so you can be at 0 degrees Kelvin and 0 degrees Rankine, there's no movement. Now, Kelvin is based on the Celsius scale. So if you go 1 degree up in Kelvin, same as 1 degree up in Celsius. Rankine is the same as Fahrenheit. So 0 degrees means no movement of atoms. If you move 1 degree up in Rankine scale, you move 1 degree up in Fahrenheit. Okay. Now, of course, do I remember what the temperatures are? I don't remember the temperatures for either of them. It's 278 or 79, and I don't remember which one it is. If it's Kelvin or Rankine. Actually, that's probably Kelvin. I don't know, but it's one of them.
Kelvin is 273.
Oh, that's the Kelvin one. I don't remember the Rankine one. Then that's the 450 something. Yeah. So there are two of them, and I don't remember either of them. Really. Okay, so nominal categories. So you only know set inclusion. Ordinal, you know, you can put in categories and it has an order. Interval, you can find differences, but there's no natural zero. Ratio, not only do you have differences, but you also have a natural zero. So examples. For nominal level data, well, zip codes. Zip codes are nominal. There's no order to zip codes. If you've looked at zip codes, you know, they're all over the place. You can't, you know, your zip code for you and the guy maybe once you cross the street look totally different. And so zip codes don't have any real order to them. But you can tell what zip code you're in. There is actually a slight, for my father used to, for a few years, work with, he was a baggage handler for, what was it called? The post office. So he actually, there is a slight reasoning behind zip codes. You know, so you could say, oh, I know this is from this state and this would be in the north, blah, blah, blah. So there is some really complicated way of figuring out zip codes, but there's no order to it. It is there is an algorithm that's sort of complicated algorithm for it. Gender. I only know if you're male and female. I can't put an order on you. Eye color. Political affiliation, I can tell you what political affiliation you are in, but I can't give an order to it. Religious, your major, your mathematics, computer science, etc. Your nationality. Ordinal, so examples of ordinal level data, grades, you know, ABC. You know, maybe you're judging, you've gotten the first place, second place, etc. Ranking, you know, poor, good, excellent. Ranking of tennis players, you know, you're the best tennis player, second best, etc. For interval level data, SAT score. So your SAT score, well, for your SAT score, you can say that a person who got a 550 had a score that's 100 points better than someone who got a 450. But a score of 0 doesn't mean that you had no score on the SAT. As a matter of fact, if you leave the SAT completely blank, you get a score of 400. So if you just write your name down and you leave, your score on your SAT is 400, not 0. You get from the 400, they either go add points up or down, depending on if you get correct or incorrect answers. So.
I had a question.
Yes.
So for the interval, it's basically like a high, basically like going high on the score or being able to put them in order, because basically interval is putting nominal and ordinal together.
Well, not only can you order it, but I can also tell differences. So in other words, I can say you scored 20 points higher than the next person. Okay, so not only can I say the order, right? But I can say, well, there's, you've done so much better than the other person. You have 20 points more than the other person. So I can take differences. I can say that a score of 520 is 20 points higher than a score of 500. Okay?
Okay.
So not only can I do the order, I also can do differences. But 0 doesn't mean none. Okay? So IQ scores. Does anyone know what an IQ score is? What an IQ test is?
Intelligence quotient.
Yeah, the intelligence quotient. So it's intelligence quotient test. Does anyone know how that came about? So, the intelligence quotient test. So this was back, there was a psychologist back, it was around so it's like 100 years ago. So they were producing a test for innovation and creativity. And the test actually sort of failed and it sort of flopped. And so they remarketed it as your intelligence quotient. And so it's a remarketing of a failed psychology test as this is now your intelligence quotient. And then once they marketed it as your intelligence quotient, that became a standard that people then started to use to say, oh, you're this smart if you get this score on the intelligence quotient, your IQ score. And so it's a nice is a marketing scheme for something that, if you're unable to sell it, you spent a whole bunch of work on something and you couldn't sell it, you call it something else and see if you can make money from that. And so that's what happened, basically. How do they determine what your IQ score is? So they do the following. To figure out your IQ score, they look at Caucasian males between the ages of 20 and 45, I believe, in North America. They look at the average score that this group of people have done, and they make that equal to 100. So a score of 100 is whatever those particular subcategory of people did. And of course you get the mean is 100. So it's and something you don't know what it's called, the standard deviation, the spread of the data is given a value of 15. So so they basically norm the test according to this particular category of people. And then you then measure yourself from that category of people. Temperature. So so notice scores. So if I say I got a score of 50 on the IQ test, and you got a score of 75 in the IQ test, well, that's 25 points bigger. So I can say that. But if I say I got a score of 50 on the IQ test and you got a score of 100, well, I didn't do twice as good as you, right? So, a score of 100 is not twice a score of 50. Similarly, an IQ score of 0 does not mean you have no IQ. It just means you have a score of 0, right? It's notice 100 was arbitrarily chosen, and then 15 was also arbitrarily chosen to give the spread of your data. It's so that most people have scores between 85 and IQ scores between 85 and 115. So most people should be in that range. And once you get higher or lower than that, then those are the people that are not, the average. They're either above or below the average. Temperature in, Celsius or in Fahrenheit is also interval. You can tell differences. 75 degrees is 25 degrees less than 100 degrees Fahrenheit. But 0 degrees again doesn't make any sense. Does not mean that you have no temperature. Ratio data examples: height. If you have a height of 0, you have no height. Weight. If you have a weight of 0, you have no weight. Time. If you have 0 time, then you have no time. Salary. If you have 0 salary, you have no salary, so that's not good. Age. If you have 0 age, then you have no age. Okay. Sometimes we also call things by independent and dependent variables. And so these are sort of arbitrary names. Your dependent variable somehow is influenced by your independent variable. So these are the things that usually independent variables are things that you manipulate. Okay.